Hey there, everyone. Thank you for affording me some of your valuable time today and joining me in our webinar series on wind turbine data interpretation. This webinar is specifically focused on wind turbine grease analysis. So in this, we're just going to go over some of the expected testing scope and range that you would see with wind taken into account, and some of the challenges that come along with that, some of the industry things that we see. So hopefully you walk away with quite a bit of value, and we can give you some answers to some questions that you have. We'll do a Q&A session on the back end of this presentation. If you look to the panel that's located somewhere on your screens, you should see a chat section where you can type in any questions that you may have. So keep that in mind. I'll go ahead and field questions at the end, and we'll jump right into things. So my name is Joshua Walkup. I'm an account manager with Fluid Life here. I've been with Fluid Life for just over a year now, but I have had 4+ years working with owners and operators in the wind industry specifically. I used to have a position at a training organization where we offered techniques and training on the technical aspect of wind, getting into SCADA systems, electrical side of things, hydraulic side of things, mechanics, controls, and all the components that make up our wind industry and how to troubleshoot. So have quite a bit of familiarity, quite a bit of domain knowledge, and that's something here at Fluid Life that we're really proud of being able to provide in conjunction with our lubrication background. So where do we start? When you go ahead and start an oil analysis program, a lubrication analysis program, a grease analysis program, you have to take into account the data interpretation process. So that starts in kind of a 3-step setting where you have interpretation. That's where you, first of all, take the sample, make sure that it's a consistent format, you know why you're taking sampling, you know who's taking the sampling, you know in what manner they're taking the sampling consistently, and then you go ahead and you get your results. From there, you're probably going to have some questions, right? You're going to see a whole bunch of numerical values, some flags, and some comments, and there you can evaluate and generate questions about those results. So you want to take into account your knowledge of the situation at hand. So in this case, the service time, the component ages, the recent repairs and problems with that equipment. So say we're looking at a wind turbine and you're coming up to end of warranty period, for example, and you want to keep everything out in front of you. It's good to know what's being performed on site and the scope of things, and anything that you may have information that you're privy to prior to the sampling and the results coming in. That'll help you take into account any results that you do see. And then the other portion of that is adding additional perspective, right? So there's the laboratory side, like what we do. There's the equipment manufacturer side, of course, the oil supplier or formulators that are actually making the lubrication. They're going to have their own input. And then there's the reliability teams, the engineering teams that are a very large part of this internally as well on the end user side. So then you can go ahead and evaluate, you weigh your options, you make the call. That's the decision portion, right? That's where you get your response. So as a response, you can either ignore results, right, which is depending on your background and the information you have, that's a valid opinion to hold, or you can go ahead and set some actions based on any possible costs that may incur or anything that add complications, right? So once you've gathered that perspective, you can choose to monitor it, whether that's more frequently or adding advanced testing, whether that's adding some sort of work or preventative maintenance protocol, or in the worst case scenarios where you have to repair something. You can update your intervals or you can add any improvement projects. So whether there's something that you need to do to redesign the way you do things, that's a perfectly valid thing to do as well. So before we jump into anything specific to wind, let's just go over what is grease, right? In the simplest way I can put it, you're looking at a base oil. So in essence, it's an oil, but it's got its own additive packages and thickening agents that give it its unique consistency and color, for example. So when you look at grease in wind, it's pretty similar to what you have in a 320 gearbox oil, but it's got its thickener added to it. So when you look at grease, it's non-Newtonian in behavior. And that just means that its consistency is going to change when mechanical stress is applied to it. So it may have a preset viscosity. That's really important to know and everything. It's a primary component of both grease and oil, right? But it's a little bit different in application with grease because as there's movement and as there's stress that's applied to it, it's going to flow at a different rate. So looking at grease, if you're go ahead and tip it over out of a jar, it's not going to necessarily fall out the same way another lubricant would, like a regular base oil would. But the good thing about grease is that because it's unique in that aspect, you put it in areas where the equipment is not as easily serviceable, right? And with that, you can put it in areas that you can't necessarily just rip open and replace and pull components apart, right? So it's meant to stay there. And there are obviously techniques that you learn, especially in the sampling side, where consistently you can get a better representative sample. So right there, you want to look towards the load regime of a bearing. And where you'd see that is technically the hardest spot to get to, but you yield the most accurate results when you do that. So now that we've covered what grease is, I'm just going to give a general overview of wind in itself. I know some of you folks are already pretty familiar, have engineering background, have condition monitoring background, have tribology background. So this is just for those who aren't as familiar with wind turbines and how they work. Essentially what you're looking at is a device that turns kinetic energy, in this case wind, right, into electricity using the force from the blades. And the rotor is going to connect to the generator, either through a direct drive system, which is some of the newer technology that's coming out. But onshore in the current market in North America, you're going to see a lot of gearbox driven systems instead. And that gearbox is going to connect to that main shaft, and it's going to speed up rotation and allow for a smaller generator system versus something you see with direct drive with the permanent magnet generators. Essentially, that forced rotation of the generator is going to get your electricity and it's going to kick out to the grid. You know, wind's flowing across the blade, the air pressure is on one side of the blade, it's going to decrease, and then the force of the lift being greater than the drag is what's causing the rotor to spin in itself. Couple things to note about wind turbines: they operate on an intermittent basis. This can be for a variety of reasons, whether that's actually having to do with the wind or having to do with whatever market they're placed in. You know, look at ERCOT, for example, in Texas. I know some of you folks are in Texas, and you know that feed-in tariffs and some of the economic reasons and drivers for the grid also drive operations, right? And then these are affected by a myriad of things. It could be load, it could be vibration, it could be temperature, and then just the wind itself and its consistency and how it takes on the turbine itself. So now I just want to get into grease applications in a wind turbine. So when you're looking at wind turbines, they're using the same type of mechanical components as other mechanical systems, right? You have bearings, you have gears, drive shafts, their size and their operating conditions and environments are what pose the challenges not observed in other industries. So when you're in remote locations, you're far from manufacturing plants in some cases, you're far from maintenance personnel. I've been on sites where the O&M building is 40 plus minutes away to get to one of the further turbines out there. So it can be a little bit unique in some of those challenges, and that's away from the actual application portion where you're seeing what we talked about before, the heavy and varying loads, intermittent operation, extreme temps, and et cetera, et cetera. Although there's been some substantial work that's been done to improve, wind turbine gearbox and hydraulic lubricants and all those things that are in the drivetrain portion and the braking portion and the pitch portion, not a lot's been done on focus on the grease, right? And that's the unique thing that will present a challenge later as we move to more technologies with direct drive, when you're replacing that gearbox and the oil in it and you're switching to more bearings and more grease, right? Another challenge that's associated with it is just you measure the metrics of grease a little bit different than other lubricants, and you test a little bit different. And a lot of folks are not super familiar with that criteria. So with this presentation, we're going to go ahead and give you a baseline understanding of some grease testing that you can perform with wind application taken into account. And one thing I want to touch on as well is that your choice in grease matters, right? Not all grease is grease. There are different types of thickeners, there's different types of bases, there's different applications. Viscosity obviously is always going to be the pervasive thing in lubrication, and its flow rate and its change in conditions that affect it. Those things are just as valuable in grease as they are in oils, right? So making sure that that's consistent is a big deal, right? There's distinctive challenges because you have your size, operating conditions, location, and environment that's different. And there's competing priorities as well, right? There's cost taken into account. There's different ambient environments that are taken into account. And then with wind specifically, there's longer maintenance intervals. They're really big. No one likes climbing up tower over and over and over again. No matter who you are, it gets taxing on the body, right? So having a strong condition monitoring program, whether that's with your lubrication or any other ancillary data, that's just as relevant, right? When we talk about data in general, out of the 100%, 95% of it's not utilized, or at least not utilized with the emphasis that it's needed, right? So just keeping those things into account. So what makes a good grease in a wind turbine? There are a few factors here. I'm just going to touch on them briefly, but what you want to look for is film formation, fretting wear and corrosion prevention, EP performance, oil release, structural stability, high temperature performance, low temperature torque, grease mobility and pumpability, water resistance, and rust protection. And then I put a little guy to the left there of all that criteria, and this guy's name is application, and application is king, right? So understanding your ambient environment, say you're at a wind farm that's a lot more humid, right? Or say you don't have the service covers on the nacelle closed and you're letting dust in Texas, for example, right? And there's a lot of heat trapped inside the hub and the nacelle, right? And then also taken into account with service intervals, with current procedures that are common in wind, with how they're purging the grease and pumping new stuff in. You got to keep in mind that there could be a lot of water ingression and a lot of rust and oxidation that becomes an issue. Another thing to note is that, as I stated before, grease is not just grease. So here I have a grease compatibility guideline chart, and it's just showing you that these thickeners, they can be comprised of different components and different elements that make up their properties and what they're effective at. And that also affects if you're switching suppliers, for example, knowing what's going to be safe to put in there if you already had stuff that's been pre-greased. Say it's new equipment coming in, say it's post-warranty and you're switching to self-perform and you're going with your own suppliers, your own supply chain, there's going to be things to consider, right? So number one would be seeing what's in the thickener, right? Is it a calcium base? Is it a lithium base? Is it a urea base? Is it a sodium base? Those things matter and are extremely important so that you don't have the grease automatically rejected and you have a main bearing failure or generator bearing failure or a pitch and yaw related bearing failure, right? So here is what we would call our wind-related grease testing criteria. This is what we call our advanced test package. We do have varying types of packages that you can investigate, especially if you know, other factors like cost, of course, and scope and how you guys perform your O&M. But here we find that based on application of large diameter bearings with rolling elements, right? You're talking about tapered rolling bearings, cylindrical rolling bearings. Those applications tend to fall in line with this testing itself, right? This is also really good to give you a step in troubleshooting failure a little bit with things like the analytical ferrography. We also have further advanced testing that you can, you know, capitalize upon, or we have testing that you can do less on if you're planning on doing things more routinely as well, right? But here you're looking at confirmation of grease quality, grease stability, and grease compatibility to a degree. So here we have routine tests of color, total magnetic iron, which is our equivalent to something like a PQ index, which you may be familiar with in another world. Here, it's unique because the figures that we derive allow you to convert it to a ppm or a parts per million, which means it's a little bit more quantifiable compared to your other results in conjunction, right? Where a PQ index is kind of an arbitrary number. So it's a little bit harder to gauge the importance of. We also have FTIR identification, penetration test, unworked method, ICP spectrometry, ruler, which is remaining useful life test, and then, as I touched on briefly, analytical ferrography. So as we proceed here, guys, I'm going to go ahead and just dive into what these tests are and what they kind of encompass and things to look for as well. So we'll start in order and we'll go to color. So color is pretty much just your baseline visual cue on what's going on, right? It's important to consider when you have an environment where there's sunlight exposure or lack thereof, right? There's heat exposure, like we're all familiar with wind turbines having when they're trapped in very hard to reach areas and up tower, and say you're in the middle of Abilene, Texas, and it's really hot outside in the middle of the summer, and you got to peak in the ERCOT, and you got to get that thing going. You know, it's important to factor what's going on with the equipment itself when it's being subjected to all this stuff, right? You have water or anything else that can be, you know, contamination, any sort of wear that comes into play. Its color is going to change, whether it's going to fade or it's going to change in color as far as beyond, you know, its shade, but actually, you know, turning into something else. Say it went in as green and it came out as brown. It's just things to observe, right? Now, keep in mind, color. There's a lot of different dyes. There's a lot of different additives that are changing color of greases, right? And some of this stuff can be just natural, and some of it can be abnormal. So it's really just a rudimentary test to get your feet wet and understand that there are changes that are undergoing versus new stock base. So moving on to total magnetic iron. As I described a little bit before, it's designed to measure the degree of ferrous wear metal contamination in a sample. What is ferrous metal? It's basically a metal that contains iron. As we know, bearings contain iron content, a lot of carbon content. So you're definitely going to see some ferrous wear over the course of life in a lubricant. Steel and steel-based alloys are going to be ferrous, right? But metals like aluminum, copper, zinc, tin, those aren't ferrous metals, right? So these won't be picked up in this sort of test. It's really just looking for the ferrous wear. The TMI, what's unique about it is it's not sensitive to particle size, right? So unlike something like ICP spectrometry, which I'm sure some of you guys are familiar with and we'll touch base on if you aren't, but that's got a certain limitation to what it's picking up in the instrument based on particle size. This can help you differentiate because you're looking at both of those tests with one another, right? And if you're seeing both the TMI and ICP values increase in the generation of wear in parts per million, it's likely that you're going to see a bunch of small particles that are generated that are ferrous, right? But on the other end of the spectrum, if TMI increases and there's not a change, or there's a decrease in the ICP ferrous values, this is going to suggest that a large size particle or multiple of them are going to be generated, which indicates, an abnormal level of wear versus something that you would expect to see in these figures, right? It's a great screening tool. As a part of this advanced package, you already get analytical ferrography, but it can also step you up to something like our scanning electron microscope, which is known as an SEM. And our SEM is basically what you take the ICP and the analytical ferrography and you combine them and you put it on steroids, and it can classify every single particle that exists within that sample, its distribution, its size, and then an analysis on what that is doing. And then the other thing that it does is it's going to differentiate things like alloys, whereas an ICP is only going to pick out single elements, right? So you have to do a little bit of consideration and evaluation to be like, oh yeah, there's zinc and there's copper, so I'm looking at brass. This will say, hey, this is brass, right? So it's a little bit more unique, and then it can tell you about different metallurgy, different types of steel. There's different classes, of course. So just something to keep in mind as well. So our FTIR is basically Fourier transform infrared spectroscopy. It's a method designed to detect common contaminants, your degradation of your lubricant, dilution, and additives. And essentially, the FTIR is taking a wavelength and it's turning into something that we could actually interpret and use, right? So when you look at FTIR, it's exposing a sample to infrared. The light is absorbed by the sample, which causes the molecules to kind of vibrate and excite. And then the detector is going to record all energy that makes it through the sample. And then the result is this spectrum generated on a graph that you can see here to the bottom left. And it's basically telling you the absorbance at a certain wavelength. So that's going to give you a distinctive thing. Think of like a fingerprint in a database for criminal justice system, right? Where they can take down a fingerprint, it's in the database, and now they can identify people in crime scene investigation if there's a history link to it. So this is a great way to look at your old versus your in use, or I mean your in use old versus your new. And then also looking for certain characteristics of degradation and contaminants. So you could spot glycol if that was an issue in a different component, for example. But using wind as an example, you're going to spot oxidation and other acidic byproduct based on reaction with them. I always think of Dr. Seuss in his old books, and if you were a tribologist, I think you'd probably draft a book on FTIR and call it Ox, Nox, and SOx, right? So you're going to get values of reaction with oxygen, oxidation, ox, your reaction with nitrogen, which would be nitration or NOx, and then your reaction with sulfur, which is SOx, right? So looking over here to the right, you can see oil service hours and the oxidation by our direct trend method. There's basically two types, subtractive and then direct trend. We switched over to direct trend, just seeing that the values were a little bit easier to convey to our customers, right? But it's a little bit easier to trend that data this way. And you're just going to look at your old versus new and the effects, and we chart it out for you. And we also publish in our reports the raw data values with flagging associated with it. So penetration unworked. This is a pretty simple test in itself. You're determining the consistency of the grease, and you're measuring in tenths of a millimeter. That's a cone is basically pushed through the grease sample in something you call, strokes that are done. We do the unworked method, but there's three other, which is unworked, worked, and then prolonged worked. So depending on the scope and scale, you can look to us or to other resources, especially in more advanced testing. But essentially, you have a chart of the NLGI consistency number. NLGI is the National Lubricating Grease Institute, and they've associated values in a grading scale based on the application of the grease. And this is just a great identifier. So basically, you're saying, hey, I got a NLGI grade 2 consistency grease from my supplier, and in use in operation, a year down the road when I'm doing a maintenance cycle and I'm looking at it, is it still a 2 or has it degraded? And then it's also a great way of, if you have multiple types of greases, multiple lubrications with different properties, to make sure you're not mixing them as well, right? These are going to be prone to change. That's just the nature of heat and degradation, oxidation, and all the things that we've discussed before in this presentation. So it's just a baseline to kind of understand what's going on there. And now we have spectrometry by ICP Instrument. So for those of you who aren't familiar with ICP, you have a instrument that takes this stuff in and essentially is vaporizing the sample, and it's reporting its elemental composition in parts per million, right? So you have different elements that may serve as additives in your grease. That could be, detergents, antioxidants, anti-wear, anti-whatever, et cetera, et cetera. And these additive concentrations are mainly used to identify relation changes. Maybe there's cases of lube mixing for whatever reason. And this is a great way to establish kind of a baseline and a great way to identify things like, oh, this is what my supplier said it is. This is what we're seeing as far as its composition and the thickeners that may be involved. It could be a great way to identify, briefly iron content, for example, or tin content, tin or chrome, or things that we tend to see in results with wind specifically. Just keep it in mind that wind turbines, since they're serviced and sampled less frequently, especially on the grease side, it's harder to get trending data by the time that lubricant is changed out, right? So with grease, you're purging and you're re-greasing, you're doing those things during your maintenance cycle. And sometimes if you're not testing frequently enough, or if you're not doing comprehensive enough testing, you may not get the value that you desire out of it, right? And that's a big deal. You're talking about tens to hundreds of thousands of dollars that are on the line on multi-million-dollar equipment, right? We all know that it takes time to gather resources and budget appropriately, and those things are planned at the beginning of the year and expected, right? But with challenges in supply chain and challenges in finding, exterior services in a timely manner, this stuff becomes a bigger challenge, right? So doing the right stuff on the front end is going to help you on the back end. And then the same goes for any type of testing. If you're given garbage data, you're not going to find any great results either, right? But one thing to keep in mind outside of monitoring the presence of wear metals and changes in your additive levels and formulation changes, you have to keep in mind that spectrometry is a little bit limited in its ability to analyze larger size particles, right? So wear particles analyzed in the ICP are limited to around 5 micron in size. So if we're just stepping back and taking an example of what that means to scale, you're looking at about 40 to 50 microns is the human eye can visibly see. That's like a hair follicle, right? So you're talking infinitely smaller size, and things that you'll see that will pass through a filter maybe, right? But it's not necessarily going to catch the large size wear. So taking your different instrumentation and the testing criteria and keeping in mind that it's a holistic picture is what I would advise, right? There's of course other types of wear metal analysis tests that can be performed, and we'll touch base on analytical ferrography as a part of this routine scope a little bit later. And TMI, of course, is a great way to identify some larger particle sizes, because it'll show up there, as we discussed before. So moving on to the ruler test. The ruler test is the remaining useful life evaluation routine test, right? So essentially you're monitoring the remaining antioxidant concentration in lubricant. And when you monitor that antioxidant level, the oxidation process of the turbine lubrication can be better understood and predicted. So testing grease conditions, it means understanding the state of its physical and chemical properties, of course, and whether you're looking at extending or changing out your interval and seeing if you can stretch that out, and say you're having trouble with getting lubricants on site from your supplier, and knowing the condition-based parameters instead of just time-based parameters, which I think everybody's moving to in wind, especially because it's the hot thing. Whether that's looking at your vibration data, whether that's looking at temp data or infrared or anything else, right? This is all taken into conjunction with one another. But a great way of seeing that is looking at your lubricant degradation and formation of varnish, and the things that turbine systems are subject to, which is the effects of oxidation, and you're looking at viscosity increases, acid formation, all those things, right? There's of course loads of antioxidant additives when it comes to turbines, but this ruler test is really monitoring that remaining concentration of the antioxidant, right? So when you monitor that, you're getting ahead of it and you're able to predict its life of what it's effective at doing, which is neutralizing those things, before you start seeing additive depletion. And when you're looking at conventional tests like your kinematic viscosity, your total acid number, your FTIR data, your ICP, all that stuff, those are going to measure the extent of that degradation after it's already occurred. So this is just something that gets ahead of that. And when you're looking at different types of greases, of course they've got a whole bunch of different additive formulations. Some of them are meant to drop out, of course. This is just looking at that before you even start seeing that. So this is where you get really fancy with some of the testing. So analytical ferrography is essentially our forensic science analysis of wear particles. So you're looking at contaminants and lubrication degradation as well. And by interpreting the debris on a ferrography slide, you're going to see the color, the morphology, the size, the surface detail of ferrous and non-ferrous wear particles. So experienced analysts can provide accurate information about the type, severity, and root cause of normal and abnormal wear. You know, at Fluid Life, we have these senior analysts that are going to provide a detailed report accompanying stuff like you're seeing on this slide here with particle identification and the different classifications of such. So, you know, the benefits of this is when implemented correctly, you get a powerful diagnostic tool for your maintenance program. You get a progressive extension to your conventional sampling program, and then you get excellent return on your oil analysis investment, right? This stuff is cheap in the grand scheme of things, but you know, when we get into that mode of let's look at our lubrication, oil analysis, grease analysis programs, sometimes we're like, oh wow, that's kind of costly for a set of tests. So knowing what goes into the testing itself, the resources dedicated to analyzing this stuff, is a great way to kind of draw you back and say, okay, this is an insurance, a quick insurance investment, right? We can look at these things and we can spot laminar wear as it's starting to occur, rather than after a main bearing, for example, fails out, as they tend to do, especially on certain platforms that will not be named, because we're not here to bash manufacturers for things that are just natural in the real world, right? But when that main bearing goes, you're probably going to see, you know, something lubrication related or wear related, and you can spot a lot of that in your lubrication analysis. So how this works is during the creation of a ferrogram, ferrous particles are going to deposit on the slide, and according to the particle size, non-ferrous particles and contaminants will also deposit. So, you know, knowing the nature of your abnormal wear and contamination in the lubricant is obviously pretty valuable. A maintenance technician can make, you know, a course of action, and you can adjust or optimize your intervals or your service type and scope, and you can deploy advanced systems to kind of counteract what you would see naturally. So how can we help you guys? Obviously, we're a laboratory services model. We also have reliability resources that you can utilize. We've got people that have been there, that have done that have had experience on these platforms, that have physically been up tower, done retrofits, taken samples, right? We've got capability to offer a little bit more than just the sample itself and the results thereof. In addition to what you see in this test package, like I've discussed before, we can upgrade tests, we can downgrade tests, we can add additional a la carte, kind of like the SEM tests that I touched on briefly. We could offer training resources, whether that's through an account manager like myself or through our reliability team. We have a trainer named Drew McRae who's really great. He knows what he's talking about when it comes to lubrication. And then we also offer data interpretation one-on-one. We can go over results with you. We can schedule meetings, and we can offer some of that added value than just staring at a report with some flags on it that you may or may not be able to make heads or tails of. And then as far as reliability services that we offer outside of private training, we can do benchmarking and audits where we'll go to site and we'll see what currently exists in your scope and make suggestions and write up a report and tell you to where you can make those changes, whether it's something as simple as upgrading your filtration setup, for example, or going ahead and adding different ports and making it a little bit easier to take samples or service, or anything else that's encompassed within that. We'd also offer optimization and improvement programs, and then we could do advanced analysis, such as post-failure analysis and things like that, that can really help you guys get your feet underneath you when it comes to operating. Because we know lubrication is one aspect, and of course it's extremely important from our perspective. We also realize that operation is king, and there's certain parameters and certain discussions that take place that take precedence, right? So being a part of that conversation and being your partner is a lot better than just spitting out a report, handing it to you and saying, do what you want with it. So guys, thank you so much for joining me. I appreciate your time and effort. Of course, I'm familiar with some of you folks that are attending today, so I will send out some private messages and touch base with you, especially if we can offer any assistance. And here is where we come upon the Q&A section. So if you look to your tile there for this webinar, there's a chat window. And if you have anything that you would like to ask a question about, or if I happen to not be able to know the answer, I can get back to you or direct you to the right people who can answer the question for you. So I'll give everybody a few minutes to just type something out if they desire that. If not, then we'll go ahead and get you guys back to your very busy schedules. Once again, just thank you so much for joining us. So I'm fielding a question here that says, where do the contaminants come from? Sodium, potassium, silicon, in the ICP test, and how do we interpret these? Well, sodium, potassium, and silicon, it really just depends. With potassium, you're not necessarily going to see a lot of, things that would be attributed to it with, coolant, for example, or inhibitors to coolant, because it's not necessarily near all the cooled systems most of the time, especially in certain platforms that I'm pretty familiar with. But what you can see is some ash and some dust, and things like that can be exposed to it with potassium, because you can have hatches open for heat, or say your fans aren't working, depending on platform for the turbine. So there is a potential to see potassium ingression, but it's probably a little bit less common than, say, your sodium, for example, can come from water ingression, because if there's ambient temperature changes, these are up tower in the air, you're going to see some of that stuff. Silicon, you're definitely going to see that, because that's alloyed steel as far as a wear metal is concerned. And then same thing, silicon and aluminum is a lot of the times attributed to dirt ingression, and just natural contamination is going to happen. So that's how we can offer our value in terms of interpretation, is we know where some of this stuff comes from in a general sense, and I'm applying it to the application that exists. So I have another question that says, if we're running two different types of main bearing greases on a site, is there a way to tell using testing which grease is performing better? Well, yeah, as a part of our testing scope that we've discussed earlier, you're going to see things like your contamination and degradation, oxidation. Those are going to be pretty telltale signs. When you're looking at oxidation, for example, and how it's resisting, that rusting or that corrosive element, that acidic byproduct that's developed, right? That's going to tell you which one is better as far as handling its length of service, right? We're talking biannual, maybe annual servicing schedules. So if your grease is showing too much oxidation too quickly, or it's showing that its quality of antioxidants and concentration is falling more quickly, then that is definitely something you can identify. And then also looking at say your penetration test, for example, that we discussed before. If it's changing in consistency too frequently and you're seeing a trend where it's doing that, then that might be something to draw attention to. Now, we're not going to outright just tell you, hey, this lubrication is inadequate, you should go with a different supplier, because frankly, that's a decision that you guys should be making with your money, and of course, the operation constraints and other things that take place outside of just our raw results are frankly not going to tell the whole story, right? So there's other things to consider, of course, your other ancillary data, and then using that in conjunction with our reports is how you're going to make budgetary decisions. But absolutely, there are some ways to kind of see the differentiation between two different types of main bearing grease. Are most greases electrically conductive and insulating? Is this a consideration for choosing greases? Now, what I can say is there are definitely electrically conductive greases, and as we know, there's issues in wind, like you know, the static that comes off of there, especially with wide edge cracking and some of those issues that we tend to see. There's carbon, there's all sorts of issues that could be related to the operation of wind, right? I can't speak on if most greases are conductive or insulating. I do know you tend to see that as a general rule in operation of wind turbines, that you're gonna see instances of that and cases of that. And I can't necessarily point out if it's a direct formulation issue or anything like that. But I would definitely say ones that are more conductive can offer up some sort of issue in some cases. So it's definitely something you should consider. And I can point you in the right direction as a resource who could probably speak with more authority on that specific question. So I think that pretty much sums it up as far as questions go. Of course, if there are any other questions that you have in addition to this, I can follow up with you privately or discuss this on a call or anything like that. I'm willing to devote my time to help be a resource. That's what we do here at Fluid Life. I wish you guys the best day possible for the rest of the day, and hopefully I have the same day. Well, take care, everybody, and thank you again.